Hi guys, welcome back. So today we're going to try and derive Snell's law using a very simple set of equations that you're all quite familiar with. And we're going to start off with something very basic from year 7. Distance divided by time gives us speed. Now at GCSE level, a lot of you would have learned car tower. And you would have been able to calculate various angles and lengths within a triangle. Now we're going to use both of those ideas to derive Snell's law. All right, so let's see if we can get there. Now it should only take a few minutes, but just bear with me as we go through. Now there are key things that when you look at this idea and you're looking at various explanations, it's knowing what the wording means. So if we have our barrier between two different mediums and we've got a wave entering at an angle to our normal, all right, remember working with something approaching at the normal, very straightforward, very easy, doesn't take much effort to go through that. Now the first thing we need to know is the time it takes. When we make reference to time, what we're talking about here is the amount of time it takes for one wave to pass the boundary. Okay, so that's the first thing that we're considering, the time it takes one wave to pass the boundary. So if we think about a single source of a wave, based on Huygens' principle, we know that each wavelet produces sources of oscillations which will then generate secondary sources. Okay, so based on this idea, we can look at this distance over here and we're going to label this distance as D1, and we're going to label this distance over here D2. Now we know that the wave moving in this medium over here is going to have a certain velocity of v1, and when it arrives at this medium, its velocity is going to be affected by the change in density of the medium. All right, now what can we take from this? Well, the first thing that we can take is a very straightforward idea, and you can already see where this is going, that the value of d1 over v1 will give us the time. And we also know that if we connect d2 over v2, we're also going to get the same time because we're talking about the same wave. Therefore, based on this ideology, the first thing that we can actually do is we can say, okay, well, based on this ideology, d1 over v1 is equal to d2 over v2. Now already you can start to see a connection, and this is absolutely brilliant that we can do this, because based on this idea, therefore, what we can say is that v1 over v2 is equal to, just move that over a little bit, is equal to the same ideology of d1 over d2. Now, for those of you that can already start to see this connection, you can see that by putting this bit together, we can change these letters to say that the speed of the wave in the air, particularly if it's a light source, and the speed of that same light source in the medium, C1, which is our V1, and V2, which is our C med, which is the medium speed, is going to give us the refractive index of the material. Okay, so you can see we're already getting there very quickly, but that isn't the entire story. So let's carry on. If we come back to the triangle over here, we can see, oh look, here we go, here's our angle theta 1. We've got our angle over here, which is theta number 2. And what we've also got, if you can see it, and we'll start with the D triangle so you can see it a bit better, as well as the theta angle, you've got your right angle here. Oh look, you've got your opposite there, you've got your adjacent there, and you've got your hypotenuse. Now, what we're talking about here, because again, the lengths are really important to note. This value O here becomes our D2. Now, we're still missing a little bit of information. And the one that we're going to refer to here is H. We refer to it commonly as W, and it's the width of the wave at the medium boundary, okay? Now, I know that's quite a lot of information to absorb, so if you need to pause it and just recap what we've just done there, feel free to do so, all right? What we're going to do now is say, okay, well, based on this ideology we have here, if we label this value up here as W, the source of the wave, what we now have is a situation where we're saying, okay, well, I can use this setup over here, and I'm going to say that sine theta is going to give us the opposite over the hypotenuse. And let's make that connection a little bit further. It's actually going to be our value of O, which is our D2 value, divided by our value of H, which is W. Now this sets us up really, really nicely, okay? So what we're going to do now is we're going to progress that idea moving forward. So we carry on. Go. So now I've done that ideology, and now I can see that if I have D2 over sine theta 2, and we'll just add the diagram back in a minute so you can have a look, which is equal to our value of W. Now, if it's true on that side, if we just come back to this diagram over here a second, we're just going to enlarge that a little bit so you can see. If D2 divided by sine theta 2 gives us W, the value of W on this side, which is also, remember, based on Huygens' principle, the width of the wave at this particular boundary, then you've also got D1 over sine theta 1 is going to give you the value of W. So we'll just put that down. Okay, so as well as this ideology we've taken, we can also say that D1 over sine theta 1 is equal to W. Now that we've got those two equations, because they equivalent to the same numerical value, let's put them together. Apologies guys, still getting used to having everything angled at the correct position, especially when we have a lot more work to write down. So there we go. Now you've got this ideology, all right? Now, if you have a look, and this is really where it gets very, very cool, is we can now make this rearrangement of D1 over D2 is equal to sine theta 1 over sine theta 2. There's your Snell's law. But how does it link to the other resources? Well, if we come back over here, and we put these in our mix over here, and we just move back a little bit, there we go. There's our connection of D1 over D2, which is equal to V1 over V2, which is the same as calculating the refractive index, which allows us to make this final connection here of N2. However, we've taken it that N1 is the numerical value of 1 when you are talking specifically about air. All right, guys, so hopefully you've been able to follow that. I know it's quite a lot to take in all at once. Pause it, stop it, email me if you have any issues. Great work, guys. Thanks for listening.